I'm going to start by giving, I guess, some forward-looking statements here, so disclaimers. I'm going to start by giving a description of our company. So not everybody may be familiar with our company. Our company's Western Digital. We're located in San Jose, California. We're a global company. And I guess the easiest way to explain what we do, we provide mostly storage. So let's say, of the three sort of pillars of compute, let's say, of IT infrastructure, the compute, the storage, and the network. We're mostly in the storage domain, and we store roughly half of the bits in the world. So for all of the data that you guys collect, roughly half of those bits are stored on our devices. So I have a list there of the types of devices we provide. We started off, a lot of our team members came from IBM, so there was a division of IBM that was split off and eventually became Western Digital. So we make hard disk drive technology, and we also make NAND flash technology and solid state drives. So those are our two sort of principal components. We also, from those devices, we build platforms and systems, and we provide sort of broader solutions to various parts of the ecosystem that are sort of listed below. So that's kind of a description of our company. And I'm going to sort of give you an overview of some of the technologies that we're working on and the future of those technologies. So I'm going to start here with a statement about data. So obviously, one of the features of our world is the importance of data, and in particular the advent of machine learning. A lot of companies trying to collect a lot of data. And with machine learning, they're able to extract value from their data that we're not previously able to. And this sort of leads to this growing demand for stored data. So this picture on the left here shows the approximate breakdown between when things are stored on hard disk drives versus things stored on solid state drives. Solid state drives built from NAND flash. So it's about, let's say in terms of the amount of data stored, it's still about 70% stored on hard disk drives. If you look at sort of enterprise or data center, the big data centers across the world, it's a larger number, maybe 90% hard disk drives. So I think, just to make you aware, for, a lot of people hard disk drives are not regarded as the most exciting technology, but they're still sort of a fundamental building block of our IT infrastructure. And there's a lot of research and development that still goes on in the hard disk drive space. And some of it is actually very exciting technology, so I'm going to describe some of that. The other thing to note here with regard to these technologies is because there's sort of research and development going on in both types of technologies, the cost per bit is coming down in both cases. And so this graph shows the cost per bit for solid state drives versus the cost per bit for hard disk drives, and there's still roughly a sort of factor of 10 difference in terms of cost for storage. And we expect that difference to continue. And that's one of the things that's sort of driving this ratio of where people decide to store their data. So I'm going to describe some of the technologies that go into hard disk drive recording. As I said, it's not kind of regarded as like the sexiest kind of technology, but it's really, in fact, very, very difficult technology, and there are a lot of fundamental problems that need to be solved, and a lot of exciting work trying to extend this technology. So what you see on the top left here is a picture of a recording head. So this is sort of the guts of how a hard disk drive works. You can imagine, if you've seen these things, there's sort of a spinning platter. And then on top of the spinning platter, there's an arm. And at the end of the arm, there's a recording head. And the arm, the recording head sort of sweeps across the platter as it spins and reads and writes data on the disk. And in that recording head, there's a read element and a write element. So the read element is shown as a little red device there. It's a magnetoresistive sensor, meaning that as it passes by the surface of the disk, the fields from the recorded bits in the disk sort of penetrate this magnetoresistive element. They change its resistance, which can be measured. So that's how the reader works. And then the writer, you can pretty much get a sense of it. It's like an electromagnet. So essentially, you pass a current around this winding. It generates a field which penetrates the recording media and writes the bits on the recording media. So that's kind of how magnetic recording works. And there are some fundamental difficulties with extending it. So if you look over the past, this is I guess, 50 or 60-year-old technology by this point. And if you look over the past 50 or 60 years, there's been tremendous growth in the density at which we can store this information on disk drives. And in fact, if you look at the growth rate, it's as significant or more significant than Moore's law in the semiconductor space. So there's been a lot of technology advances associated with this technology, but there are also some fundamental limits. And the fundamental limits are kind of shown on the right-hand side. So if you look at the picture at the top right, there's a picture of, this is the recording media. This is the stuff where you actually store the bits. And if you look closely at it, it's composed of this sort of granular, there are a bunch of little magnetic grains. And if you think of a recorded pattern on this disk, what happens is that those grains are individually magnetized either up or down, and that's shown in either blue or red. And you can see that for each individual stored bit, let's say one of those red bits there's only a few magnetic grains, let's say 10, 20 magnetic grains. And you can imagine that if you wanted to shrink the size of the bits and store more information on the platter, that you would have a problem unless you can make those grains smaller, because eventually the recorded data just becomes too noisy. And that in itself is difficult, because what happens is as you make these grains smaller, they become thermally unstable, meaning that they will just decide to switch their magnetization direction on their own just due to thermal excitations. So there's a picture on the bottom right here showing there's an energy barrier to flip from magnetization up to magnetization down. And what happens is, as you make these grains smaller, that barrier drops, and eventually these things just kind of flip on their own. So that's bad. It means that you write your data, and then you come back a few days later, and your data's gone. So in order to solve that problem, what we would like to do is make that energy barrier bigger. We would like to make the grains, if you like, magnetically stiffer, so that they don't tend to flip by themselves. But the problem with doing that is that you then don't have enough field strength from the writer to be able to actually write them anymore. So that's kind of the fundamental dilemma of magnetic recording. That's the fundamental reason why we can't increase the areal density by another factor of 10 very easily. So there are a lot of interesting and exciting ideas to solve this problem. One of them is called shingled magnetic recording. It's actually a pretty easy concept. The idea is that if you look on the previous page, there's a right pole. The electromagnet has a right pole that comes down and drives the field into the media. So one thing you can do is just make that right pole wider. And if you make it wider, it's easier to get more field down into the recording media. So this causes a problem, though, because if you make the writer wider, of course you would expect the bit density to go down. And so in order to solve this problem, what we do is we write the tracks kind of overlapping. We call that shingled magnetic recording, and it's like shingles on your roof. So if you imagine your roof where you're putting down tiles, each layer of tiles goes down on top of the previous tile, and you can use this wide writer to write a wide track on the recording media, and then you come back later and you kind of overwrite it partially, and that gives you a very dense recording pattern. But it obviously has some problems, in particular, the same problem that you would have if you wanted to replace a single tile on your roof. You have to remove all the tiles on top of it. So there's a problem here that is solved through software and indirection, et cetera, where if you have to manage this thing in a different way. You can no longer go and randomly update a single piece of information on the disk. You have to orchestrate your writing process so that you kind of write sequentially within a zone, for example. So this is one way of extending magnetic recording areal density. There's a second way here, which is called heat-assisted magnetic recording. And this is sort of very interesting and challenging technology. The way it works is that, I mentioned this problem. You want to make these grains smaller, but you can't because they will spontaneously flip with thermal energy. So you like to make them stiffer, magnetically stiffer. And if you make them stiffer, the problem is you can't write you don't have enough field from the write element. So the way this works is that you pick a type of recording medium with a different type of material, and you select this material so that it's kind of sensitive to heat. And what happens is when you apply heat, it becomes very easy to reverse it magnetically. And when you cool it off meaning down to room temperature, it kind of becomes very stiff. So what happens is you apply heat to this thing, then you write it with your magnetic field, you change its state, and then you remove the heat, and it kind of, if you like, freezes in place. Not literally freezing, because it only drops down to room temperature. But when you write it, it's, let's say, 600 degrees, and then after the heat is removed, it kind of freezes the information in place. So this is heat-assisted magnetic recording. And the way it works, what you have to do is you basically have to take a little laser and put it in your recording head, as shown in that picture. So as you can imagine, this is a very difficult and challenging fabrication process. The recording head is already pretty difficult to make. So I don't know if you can imagine, you know, this head is made through something similar to a semiconductor process. So we use the same tools that are used in a semiconductor fab. So you use lithography and deposition and etching, whatever. And it's, you know, the way this recording head is built up is, if you imagine the surface of the wafer would be a vertical plane, and you're building from the left to the right. So you have to do a semiconductor process that builds this complicated 3D structure. And in fact, it's one of the most complicated processes that people use today. It's more complicated, let's say, than building a 3D NAND device or most logic devices. There are more steps involved than almost any other sort of semiconductor process. And it's very difficult to fabricate this thing because it has a lot of sort of 3D topology. And so now what you're going to do is you're going to come in and put a laser on top and make a little hole and fire the laser down between the gaps of this recording head. So it's actually a very difficult thing to do, but in fact it has been done. And we have sort of working demonstrations of this. The technology is not shipping yet, but it you know, holds some promise for the future. The other thing I should mention is that you know, some with physics background may be thinking, well, you know, that can't work because you have a laser and, you know, there's a certain wavelength of light, so how do you get a tiny spot on the disk? The way that it works is that where the laser, actually what happens is, I guess, you know, the two pictures on the bottom left here, what happens is you fire this laser down through a waveguide, and the waveguide sort of, you know, travels down to the bottom of the recording head, where it's right near the recording media. And at the bottom of this waveguide, there's something called a NFT, or near field transducer. And what that thing really does is it basically, you know, the light's polarized in a certain direction, so there's an electric field from the light that causes the electrons in this near field transducer to kind of slosh back and forth. And they, in turn, are capacitively coupled to the electrons in the disk, so they cause electrons to sort of slosh back and forth inside the disk material, and that heats it up. So that's how you get a tiny spot. And what this near-field transducer will allow you to do is take something which is a, you know, reasonable laser wavelength and still make a really tiny sort of 20 nanometer spot on the surface of the disk. And one of the difficulties with this technology is that near-field transducer becomes really hot, because again, you're trying to heat up the disk to, let's say, 600 degrees. So you've got this little tiny thing on the end of the recording head which is getting really hot, and you have to figure out how to build the device so that it can withstand those temperatures. So that's heat-assisted magnetic recording. It's an ongoing area of research. I'll tell you about another technology that's kind of related. It's called microwave-assisted recording. And with microwave-assisted recording, it's sort of a similar principle. The idea is that you have these, you know, grains on the recording media. You'd like to be able to reverse them magnetically, but it's quite difficult to do. But instead of using heat, instead of using the heat from a hammer or heat-assisted magnetic recording writer, you create a different kind of writer. And this writer has a little device in it, which is called a spin-torque oscillator. So a spin-torque oscillator is a device that basically, when you pass current through it, it creates a magnetic field. So basically, you pass a current through it, the current goes through a spin polarizing layer, and it picks up this spin polarization, which then is transmitted to another layer, and it imparts its sort of angular momentum to this other layer and causes that other layer to magnetically precess. So that's kind of shown on the right-hand side. What you get is a layer of magnetic material where the magnetization is kind of rotating like a top, and it generates a field, an RF field, which penetrates the recording media, and again helps you reverse the grains on the magnetic media. And you know, this has some advantages relative to the heat-assisted approach. You can imagine, for example, that it's more efficient. You know, if you're transferring heat into the recording media, it's kind of a indiscriminate way of transferring the energy. If you can, create this spin torque oscillator and get it to oscillate, and then kind of tune your recording media so that your recording media responds to a particular set of frequencies, then you can, if you like, transfer energy into the recording media in a more effective and efficient way. So you don't have to heat up the recording media quite so much. So these are the main challenges of magnetic recording. It's still storing the bulk of data in data centers today and across the world. These are active areas of research, but there's still a lot of fundamental work going on, and this is some of the techniques that we're using to extend the recording density for magnetic recording. So I'm going to switch gears. I'm going to talk about NAND storage. So some people maybe more familiar with this. I expect most of your laptops have solid-state drives in them as opposed to hard disk drives nowadays. This technology, NAND flash technology, has changed significantly over the past few years. It used to be used to have what they call 2D NAND flash, where you would essentially create a circuit on the surface of a semiconductor wafer where the kind of bits were stored next to each other. They're kind of distributed in 2 dimensions across the surface of the wafer. So the technology used today is 3D NAND flash, and this is a technology that's been adopted, let's say, over the past 3 years, introduced into manufacturing. And the way it works is you take a conventional sort of 2D NAND flash structure, and you basically flip it up so that you create something in a 3D array, as shown in the right-hand side. So this may be a little bit difficult to understand if you're not familiar with the technology. But basically, the way it works is that you have I think there's a picture there showing, well, you have these sort of vertical channels that run up and down this device, and what you do is you try to run a current through these vertical channels, and there's a bunch of transistors that are along this vertical channel that can pinch off the current. And the way you record and read a bit is if you want to read or write a single bit along this channel, what you do is you turn all the other transistors on, more or less. So the other transistors, you turn all the transistors on except for one transistor. So essentially most of the transistors are doing nothing. There's one transistor that's kind of active here that can either pinch off the current or not. And then that transistor has a threshold voltage. If that's how you program it, you set the threshold voltage. So in some cases, the threshold voltage may be set so that transistors kind of default on, which will allow the current to flow, or maybe default off, which will block the current. And by sensing whether you have a current flowing or not, you can read a single bit of information out of this structure. So this structure is also very difficult to make. You can see, you can probably imagine how you might make this. You basically deposit all of these layers of stuff, and I think we're up to at least 96 or 128 layers in most cases. And then what you have to do is you have to essentially drill these holes through it, and then fill these holes with multiple layers of different material, as shown on the left-hand side. So the left-hand side there, you have a picture, a close-up of one of these memory holes. These are the channels that run vertically through this device. And so you drill these holes, and then you have to kind of coat the side wall of this hole with multiple different, very thin layers in order to construct the transistor structure. So that's kind of how 3D NAND flash works. And this has been a big advancement in technology that has allowed the cost of NAND flash to decrease significantly over the last several years. And there's sort of, let's say, 3 general trends in this area. One of them is, we're going to more and more layers. So, you can imagine, you can think of this thing almost like a skyscraper. So you build up all these layers, and then you have to drill these long, thin holes down through these layers. But as we get better at drilling these holes, we can make more and more layers and basically store more and more bits in the same space. So that's one trend. The second trend is storing more bits per cell. So this graph here in the middle, I mentioned, the way you program these things is you control the threshold voltage in the transistor, and you can set the threshold voltage to several different layers. You can choose either to set the threshold voltage to one of 2 layers, which is shown in the top, which means that you're storing essentially 1 bit per transistor. or you can decide that you're going to try to store one of 4 layers, for example, in your threshold voltage, which means that you're storing 4 levels or 2 bits per cell, or 8 levels, 3 bits per cell, etc. So one of the approaches with this technology is to store multiple bits per cell, and we keep adding more bits per cell. Nobody knows when that's going to stop. But obviously, one of the consequences of doing this, it becomes more and more difficult to discriminate between these layers. And one of the consequences is as you add more layers, it becomes more difficult to read and write the data, and kind of takes longer. So as a result, it seems that the NAND flash industry as a general principle are sort of pursuing 2 different approaches, or this technology can be used in 2 different ways. One of them is that you can try to optimize for cost. So you can try to put as many layers as you can, and then you suffer the consequence that these things are, they may be more difficult to read or write. The other thing you can do is optimize for performance. So you can go back to storing only a single bit per cell, and then it's faster, it's less dense and more costly, but faster to read and write the data. And in fact, there's been a significant improvement in speed for solid-state disks in addition to cost. So obviously on the, there's decrease in cost, but another path that people are taking is sort of increasing the speed of the solid-state memory. And I'll get back to that point a little bit later. So these are the 2 main sort of vehicles for storing information, hard disk drive and NAND flash. I'll mention another sort of emerging category of memory or storage, which is there's a whole class of different materials that are being examined for use as a new memory technology. So the current memory technology is, of course, DRAM, which is for every cell you have a transistor and a capacitor. And with these technologies, it works a little bit differently. You have a bunch of materials that are listed here, which these materials, they have the property that they kind of can change their state, if you like. They're like resistors, but they can change their state. They can either be like in a low resistance state or a high resistance state. So the technology that I described before, NAND flash memory, the basic building block is, if you like, a 3-terminal device. It's a transistor. So it has a drain and a source and a gate, and it's got like 3 points that you have to hook up. And essentially the way you store information in this flash memory transistor is you set the threshold voltage. So the threshold voltage tells you how easy it is to turn on or off the transistor, and that's the way you store this information. On all of these other classes of materials, they're not 3-terminal devices, they're 2-terminal devices. So it's kind of like a resistor. There's just 2 terminals. And by applying current to it, you can either get it to flip to a high resistance state or a low resistance state. So it depends exactly how you apply the current. If you apply enough current, or you control the waveform with which you apply the current, you can get it to switch between those 2 states. So then it becomes, becomes a resistor that's either in a high resistance state or a low resistance state, and that's how you store 1 bit of information per resistor. So one of the consequences of having this 2-terminal-like structure is that you use a different architecture for putting together the memory. So in most cases with DRAM technology, you arrange it in this grid. You arrange the bits in a grid. And then at each cell where you want to store a bit, you have a transistor that stores charge on a capacitor. This is a different type of technology, which you put in this, arrange in this structure, this cross-point structure. So the way that cross-point structure works is there's a bunch of wires running, north, and a bunch of wires running east-west. And at every point where those wires intersect, there's a memory element. And the memory element is composed from one of those materials that I showed on the previous page. So the memory element is basically like a resistor that can be either low resistance or high resistance. But you need another device as well, which is shown on the right-hand side there. Maybe you can't read it clearly. It's called a selector. So you could imagine creating this array, as shown in the top left. If you only have a memory element at each one of these connection points, it's kind of difficult to read or write or access that single element. Okay, so the way the selector works is that it's like a valve. So you have a material that kind of turns on like a valve. If you apply enough voltage to it, it kind of turns on, allows you to individually address each cell in this structure. One of the consequences of this cross-point memory is that you need a different memory interface. So with DRAM, you use this DDR interface that allows you to read or write the memory. One of the consequences of this cross-point structure is that you need a different kind of memory interface. And this is one of the reasons why I'm going to just switch over in the last few minutes here to talk about this RISC-V technology. One of the problems that we have in the industry is that these interfaces are kind of tightly controlled by, if you make a CPU, if you want a new memory interface, you have to make a new memory that has this new interface. You also have to make a CPU that supports that type of interface. So this is a kind of restriction that exists in the industry today. And in fact, there are multiple problems that exist. One is one problem that we have today. On the left-hand side, if you want to have this new type of memory, which is listed here as SCM or storage class memory in yellow, you need a new memory interface to read or write that technology. In future, there are other interface challenges that exist that I won't go into in too much detail. But within a system, you have something called a coherency bus, which allows you to share information amongst different processors on a same system. And in order to allow you to introduce new types of compute element for machine learning, accelerators, et cetera, you would like to have a kind of open coherency bus, which doesn't exist today. And then further down the line, you would like to have to be able to extend that coherency bus outside of the system and have an open kind of memory fabric structure. So what we're doing in our company, we're supporting this initiative. It's like, if you like, an open source kind of processor architecture called RISC-V. So you guys may not be familiar with it. It's kind of relatively new. It's an open instruction set architecture. So today, there's sort of two main instruction set architectures. You have Intel and ARM. And these are, if you want to use them or make a processor, you have to get a license. So it's kind of proprietary. This RISC-V is essentially an open instruction set architecture, so you can think of it like open source software, like Linux. So this is an initiative within the industry to build up this open source hardware capability where people can essentially build their own cores using this new type of instruction set architecture. So Western Digital has invested heavily in this. We ship roughly 1 billion cores per year on our devices. So in our SSDs and hard disk drives, every device has a bunch of processor cores on it, and we're actively supporting the development of this new RISC-V sort of open community, and we invite others to take a look at it as well. And we have, built our own cores and introduced them into our own NAND controllers. So this is an active area of work for us, and if you're not familiar with this, we encourage you to kind of take a look at it and perhaps participate in it. It's an open community, kind of just like Linux community. So I'm going to skip that last page and just sort of make some, getting back to forward-looking statements here. So today we have a massive proliferation of data that's being driven by new applications like machine learning that allow people to extract more information from their data or more value from their data and encourages people to store more data. And that's one of the things that's driving our industry in particular. For the two sort of pillars of storage technology, sort of hard disk drive and NAND flash with SSDs. And we see sort of continued technology evolution in both of those areas through invention of new technologies and processes, materials, et cetera. We see significant opportunity and need for new architectures based around open, standardized interfaces. So one of the things that's kind of gating progress in the industry is the fact that if you want to introduce a new type of memory or you need a new interface which doesn't exist today, and you would need an open processor architecture to support that. And then finally, we've introduced this RISC-V, which hopefully some of you have heard of, but maybe not all of you, which is a new sort of open instruction set architecture. People are just starting to build processors on this architecture. And we would welcome anybody to join that and support us in that effort. So that's pretty much it. Thank you very much.